here, and today we have the Forum on Robotics Control Engineering online seminar with Dr. Laflito. Before we start, I'm going to talk about FoRCE a little bit. FoRCE is dedicated to provide free, high-quality outreach events and online seminars to reach broader robotics and control communities around the world. Thus, we periodically invite distinguished people like Dr. Laflito to give their talks on their recent research results related with robotic and control engineering. The aim of the FoRCE connecting academicians and government industry researchers with each other through the research and online education discussions. So we cordially hope that you will enjoy all the FoRCE events and you will find them highly valuable to your own research interests. By taking this opportunity, I also acknowledge the support from IEEE CSS, where you can find the past FoRCE talks and many other talks at the IEEE CSS video library webpage. Let me also mention about the rules. So please be muted during the presentation. If you want to ask questions after the presentation, you can do simply by unmuting yourself. And we will record this section and we will post to the FoRCE webpage, YouTube, as well as the IEEE CSS webpage. Jointly with Tansel Yucelen, we are very proud today to host Dr. Andrea Laflito. And Dr. Andrea Laflito is an associate professor within the Department of Industrial and System Engineering and affiliate professor with departments of Aerospace and Ocean Engineering and Mechanical Engineering and the National Security Institute at VirginaTech. He received Bachelor of Science and Master degrees in Aerospace Engineering from University of Napoli and Master degree in Mathematics from VirginaTech in 2010, and a PhD degree in Aerospace Engineering from Georgia Tech in 2015. His current research interests include nonlinear robust control, optimal control, and the design of control system for unmanned aerial systems. Presently, Dr. Laflito serves as the senior editor of Autonomous System Area for the IEEE Transactions on Aerospace and Electronic Systems. He is recipient of several academic awards, including DARPA Young Investigator Award in 2008. For all of you here, I would like to thank Andrea for participating in our forum as a speaker. Andrea, please go ahead and start whenever you are ready.
Thank you very much, Marv, for your introduction, and thanks to you and Tansel and those who made this event possible. I'm truly honored to be here. I've been watching this series for a long time now, and when I got your invitation, I really felt humbled, and I mean it. Sometimes these are empty words, but this time it's really meant. All right, so today I wanted to share with the community a little bit on my latest work, and so on adaptive control. And so I titled this presentation Advances in Model Reference Adaptive Control, Fast Transients, Constrained Errors, and Hybrid Systems. So a one-slide review on model reference adaptive control. It's a technique that allows, in its basic and fundamental version, to control systems in the same form as the equation we have on the first line. So it's a system for which we assume that it has a certain linearized form, AX, and A is unknown, and a second term that comes from B lambda, and U, the control input, and theta transpose phi, where lambda is a diagonal positive definite matrix that is unknown. Usually phi, the regressor vector, is known and gives us some information on the plant state, on a plant dynamics, and theta is an unknown matrix of coefficients. So we have a rough idea basically of how the system works, but we may not know what the coefficients that characterize the systems are. There are other versions way more sophisticated than this, but I wanted to present the key notions here. So the idea is to find a control input U such that despite these uncertainties, the trajectory X is able to follow the reference trajectory XREF. That is the outcome of a virtual system, the so-called reference model that you see in the second equation here. So the result is fairly popular. All you need to do is to create the control load given by the product of an adaptive matrix adaptive matrix of adaptive gains, and a vector that I usually call pi, but it's more of a notation of mine. That includes the state, the reference command input R, which is basically, if you're thinking that X represents an aircraft and X ref an ideal aircraft, R in the ideal aircraft is like the pilots controlling the ideal aircraft, and the controller has to let the actual aircraft follow the ideal aircraft. And negative phi in the term pi. The adaptive law has the standard form, and we have substantially two tuning knobs here, assuming that the reference model has been fixed by someone. We have two tuning knobs. One is gamma matrix that is of adaptive rates that is positive definite, and matrix P that is the solution of Lyapunov equation. It's a little bit harder to tune that because it's an indirect approach, because you don't handpick the solution of the Lyapunov equation. So primarily people tune gamma to tune the solution of model reference adaptive control. So there are several challenges though. First of all, gamma, yes, it allows large gamma, whatever that means. Gamma is a matrix, so we cannot say that it's large, but you know, if you choose some matrix like the value of the smallest eigenvalue or the largest eigenvalue, you try to crank up gamma so that you have a rapid adaptation. Tracking error dynamics, however, is as fast as the reference model. This means that typically, and it can be proven, the plant reaches the reference model pretty much when the transient of the reference model has died out. However, we spend a lot of time trying to design a good reference model, and then we lose the transient of the reference model, which is something we don't really like. And then the proof of classical model reference adaptive control tell us that the tracking error, which is the difference between the plant and the reference model, is uniformly bounded. We know that the adaptive gains are bounded. The control input turns out to be bounded. But establishing user-defined bounds on the tracking error and the control input is usually is not something that can be done in the classical formulation, and is a topic or has been a topic of research until recently. So there are several solutions that are extremely valuable and address several of these issues. For example, barrier Lyapunov functions have been employed by Dr. Yucelen, for example, in his group, to name one, to bound the tracking error. The projection operator is a very popular tool to bound the adaptive gains, and that helps a lot, especially in the presence of external disturbances or unmodeled matched uncertainties that I didn't discuss in my introductory slide. It's to fix the problem of the slow transient. Some people employ the observers or slightly modified the reference model to improve the convergence rate of the trajectory tracking error. Here, I'm going to present a solution that does not involve observers and does not involve modifying the reference model. So in my work, I usually assume that there's a user that provides a reference model, and we don't want to interfere with that. So we start with what I call two-layer model reference adaptive control. So I introduce a new term, a transient tracking error, which is given by the first equation on this slide. It basically helps the actual trajectory tracking error to converge to zero faster, because initially we trace these fast dynamics, and the request here is that basically the smallest, the largest eigenvalue of a transient, the real part, of course, has to be smaller than the real part of the smallest eigenvalue of RF, with RF given by the user. And then we're adding a term to the adaptive law that I marked in red. So we have the first part that is the usual part, and we have an additional term that depends on the error. And then we have our adaptive laws, where now, first of all, we don't have E transpose, to be precise, in the adaptive laws, but we have epsilon transpose, with epsilon being the difference between the tracking error E and E transient, this artificial, if you want, tracking error that we introduced. Being a transient Hurwitz, the effect of this will die out, and so eventually epsilon coincides with the E. Again, we leverage the fact that in the transient, we're following epsilon basically, so some E modified pretty much. And the adaptive law for KG looks a lot like the adaptive law for K, the classical one. So the theorem basically promises that the trajectory tracking error goes to 0, and we converge faster to the reference model than we would with classical model reference adaptive control. So I wanted to give an example. It's a classical example that I drew from Lavresky's book, Lavresky's and Weiss book, Robust and Adaptive Control, which is, a solid guideline I employed for my class, for example. So it's the roll dynamics of delta wing aircraft. Has two states, a single control input, and all the theta terms are unknown. And so we asked to follow a reference signal generated by employing a reference command input that looks like a sawtooth function that that with amplitude 0.2 and that I report in the slide. And so we have the reference trajectory. If you look at the figure on the left, there is in the state space plane red line. And then we show the trajectory employing classical model reference adaptive control and our approach. As you can see, the black line converges to the red line later than the blue line does. And then in the figure on the right, we tune a parameter that allows us to span a transient. So we show multiple results, keeping everything the same and changing the A transient matrix that allows faster convergence. And so for multiple values of sigma and hence for different values of the A transient matrix, we can see that the tracking error converges to 0 faster and faster. Clearly, as we always say in controls, there's no free food. And so this comes at the cost of a more aggressive behavior that, for this example, resulted in larger tracking error in the transient. So the next thing is to try to fix this issue. And so we go into the next part of this work, and it's what I usually call a model reference adaptive control for prescribed performance. And so we want to impose two kinds of constraints. We want to impose a constraint on the tracking error and a constraint on the control input. The constraint, both sets of constraints are captured by sets whose boundary is captured by this scalar valued functions he and hu. The requirement is that within the set he and hu are positive, and so you may want to imagine he and hu like some domes, some upside down balls, centered usually, doesn't have to be at the origin of the tracking error or at 0 control input, and they are equal to 0 again at the boundary of the constraint set. So long story short, the control input we employ here is very similar to the classical control input of adaptive control. So there's the usual part K transpose pi with the same pi as we seen earlier, and a second term that we present as K transpose G times G. G is a vector function that is user defined, and I'll spend a couple of words about it in a minute. And the adaptive laws are those shown in the figure. Now, if we do a very simple and quick exercise, we find out that if, for example, HE is identical equal to 1, so basically we're setting no constraint on the tracking error, HE prime, which is the derivative of HE with respect to its argument, is equal to 0. And so the first law reduces to the classical classical adaptive law of model reference adaptive control. If HU is equal to 1 as well, and we forget the term in brown that we have over there, we'll discuss it in a second, in the second adaptive law. Also, this adaptive law reduces to a classical form of MRAC, or an adaptive law for MRAC. So a few concepts. I didn't mention that M is a non-negative definite matrix, and we use it to give different weighting to the penalization of E. So, for example, we may be interested in penalizing only one of the entries of E or some more than others. Anyways, a few comments. Although we mentioned that G is user-defined as long as its Lipschitz is continuous, anyways, subject to the the usual regularity conditions, setting G equal to E allows to account for the tracking error in the control input and not just in the adaptive law. And as we saw earlier, it enables the two-layer formulation, and hence it allows to regulate also the transient dynamics with the due modification to the adaptive law. Something interesting is that, as we would expect, HU and HE have competing objectives. In fact, if we go back to this slide and we look at the second adaptive law, we see that HU squared is at the numerator and HE is at the denominator, which makes sense because typically higher precision, tighter constraints imply or may imply stronger control input. At the same time, instead, having weaker control input, if you like, typically may lead to larger errors in the control in the trajectory tracking error. So of course, there are competing objectives that are captured there. And because we are explicitly trying to constrain the control input, we need to introduce some kind of observer of the derivative of U. We don't have U dot explicitly, so we can only estimate it. And this work allows to use some differentiator of our choice. For example, we used a traditional one. For example, we used an impulse response filter. But as long as we're able to capture the derivative of U through the form gamma transpose HD, which plus chi with chi unknown, it's not, our formulation works fairly well. And chi is treated as an unknown, as a parametric uncertainty. Again, as you can see, I'm going not too much into the technical details. I'll be happy to discuss them at the end of the presentation and to refer you to the journal publications underlying this work. But right now I wanted to highlight how this has been put in practice. So we have an aircraft that is a so-called tail-sitter or quad-biplane. Basically, it's like a quadcopter and has two wings so that it takes off, lands, and hovers just like a quadcopter. But then by doing a pitch maneuver, it is able to fly horizontally and exploit the wings to sustain itself. And the advantage is that we get longer endurance because in horizontal flight, we're able to cover long distances without spending as much energy because the wings do the job of keeping the aircraft in the air, which is usually more efficient than using propellers. Equations of motion for the longitudinal motion of this vehicle are given by the classical form given by Newton's law. We account for lift and drag, and we assume that we know the parametric shape of lift and drag, but we don't know the aerodynamic coefficients. And then the rotational dynamics is the classical Euler's law in the plane, with My being the control moment and Ma the aerodynamic moment. So we divide the problem as usual in outer loop and inner loop because we substantially have 3 degrees of freedom, x, z, and theta, but we have only 2 control inputs, which is, in this problem, the total thrust and the difference between the thrust of the motors on one side and the thrust of the motors on the opposite side, which give us the control moment for the vehicle. So we massage the equations a little bit and we put them in a classical form of model reference adaptive control. And the outer loop control input is given by the horizontal, the force, the desired force in the horizontal plane and the desired force in the vertical plane. The negative sign comes from the fact that following the aeronautical convention, we set the z-axis positive downward. So we employ, or as you'll see soon, we will employ model reference adaptive control to define these 2 forces, and hence we're able to deduce the desired pitch angle that we call theta command, that allows us to follow the to point the propellers in the right direction and hence generate the desired thrust. This formula here, the theta command, is the result of an optimization problem where we want to find the least theta that allows us to realize the horizontal and vertical components in the global frame of the control force, while never putting the nose down. For safety reasons, we don't want to have the thrust vector pointing down, which means the propeller is pointing down, so that in case of emergency, we're able to pull the aircraft up again and have it hover instead of having it go actively toward the ground. The inner loop dynamics then again can be reformulated in a classical MRAC form, and the task now is to follow theta command. So we integrate inner loop and outer loop to make sure that we don't have problems of instability of cascaded systems given by the usual arguments about the basin of attraction, and then model reference adaptive control or any of its variants, as some of which we have discussed earlier today, will give us U outer and U inner, and hence we're able to generate the thrust force T hat. Now we need to be careful about T hat. It's not so the way T hat is generated is the following. If the aircraft is pointing its x-axis, which is the axis of the propellers, not too far from the desired direction, hence that those conditions on theta command minus theta in absolute value minus 10 theta max, then what we do, we exploit the projection of the thrust force along the desired direction to let the aircraft move on. If the x-axis, the axis of the propellers, forms an angle that is too large with respect to the desired direction, imagine, for example, the aircraft is going totally in the wrong direction, so we're supposed to point the propellers in the opposite direction, then in that case, we generate the nominal thrust, which is the third case, primarily to control the rotational dynamics, point the aircraft in whatever direction it's supposed to be pointing, and hence work on the tracking. Clearly, again, we can only work on it in terms of an approximation problem because we don't have enough degrees of freedom for this vehicle, which, by the way, does not have ailerons or other mobile surfaces. Hence, having established the hat, we generate we compute the moment, the force that a set of propellers, let's call it T upper, has to generate, and the thrust force that the other set of propellers is supposed to generate. Again, depending on the attitude of the aircraft and the various moments of the vehicle. So we apply here the so-called model reference adaptive control for prescribed performance in simulation. Produced in MATLAB. We give a reference trajectory that is not optimized for this vehicle. We assume a NACA 0012 airfoil, and the reference velocity is purposely designed to be too fast, so the aircraft is not able to fly horizontally at a constant pitch angle. So it has to adjust the pitch angle to maintain the desired altitude and at the same time go forward at the user-defined velocity. Clearly, if the user puts effort in designing a good reference trajectory, the vehicle would oscillate less. Here we have a comparative analysis between a classical MRAC and performance MRAC or constrained MRAC. And as you can see, the blue line stays way closer to the red line, the user-defined line, than the black one. And if you do a zoom in at the end of the mission, in which the aircraft is supposed to come to a halt almost instantaneously, but at least very rapidly, you see that both controllers need to fight a little bit the fact that the aircraft was moving forward at a low pitch angle, and using our formulation of MRAC, we're able to reduce considerably the oscillations compared to classical model reference adaptive control. Here are a few plots showing the tracking error, and as you can see, applying the proposed approach, the tracking error is always below some threshold given by the pink line. Same thing for the inner loop. These are simulation results. As we speak, some of my students are working on experimental results employing similar controllers, slightly more advanced versions. And I'll discuss these controllers in the next part of the presentation. So the second piece of work I wanted to talk about is model reference adaptive control for switch systems. So there are situations in which the A matrix, the B matrix, the phi vector change instantaneously. This happens when, for example, if we're talking about aeronautical applications or industrial-like applications, when you do payload delivery, for example, you may be dropping some payload instantaneously. So some properties of the vehicle, inertial properties, change instantaneously. But other classical examples are given by instantaneous changes in viscous coefficients or roughness coefficients when you go from static to dynamic contact models, for example. But again, the examples are plenty. And at the same time, the user may want to change the reference model instantaneously by changing RF and BRF, however they like. So we assumed in this study that A is unknown, theta is unknown. The mapping between sigma and A is unknown, and so the mapping we don't include a mapping between sigma and theta in this model just because through a simple trick we can always create a bigger theta that accounts for all the theta sub sigma, basically. So it's quite without loss of generality. A few words for those who are less familiar with this kind of systems. We cannot use the classical solution as is, or at least we need to think about the notion of solution for this kind of systems. And so there are substantially two very popular solutions, at least. They're not the only ones, but they're fairly popular. One is the so-called characteristic solutions that are absolutely continuous functions given by the initial condition plus the integral, the Lebesgue integral of the differential equation, or the so-called Filippov solutions that are definitely more articulated, but at the end of the day, they're checking the closed convex Hall given by the vector field by excluding all the sets of measure zero and observing the behavior on multiple balls of different radius. That's butchering the meaning of it, but I'm trying to give just an overview of the meaning here. And again, also Filippov solutions are absolutely continuous per definition. So what we do, we prove that we can use a control law that has a form that is extremely similar to the classical one, an adaptive gain times the regressor vector that is slightly massaged. The script I function that is described at the bottom basically tells us what mode is being activated. The cross with the circle around denotes the Kronecker product. And we have an adaptive law that is very similar to the classical adaptive law. So we try in my group to produce adaptive laws that one way or another can be reduced to the classical MRAC under due simplifying assumptions. We solved the problem in two frameworks, the carateri framework and the Filippov framework. And in the carateri framework, basically P comes as the common Lyapunov function, the matrix Lyapunov, the positive definite matrix that solves the Lyapunov inequalities given the whole equation on the screen. And so we use the approach of the common Lyapunov function. Some later work will discuss briefly remove this assumption and rely on the so-called dwell time, which is the minimum time between two switchings. Well, we'll discuss this later. And to do so, to obtain this result, we extended the LaSalle-Yoshizawa theorem to the carateri framework for switch systems. And then in the Filippov framework, the result is extremely similar. The only difference is that whereas in the carateri framework, we're able to prove uniqueness of solution, in the Filippov framework, we can only prove the existence of solutions. Using substantially the same adaptive law, in the carateri framework, we need to impose that the dwell time, again, the minimum time between any two switchings is always greater than 0. In the Filippov framework, we're able to bring TD in the limit, the dwell time in the limit to 0. And so we go back to the canonical example of delta wing aircraft. And in this case, we imagine the aircraft being able to switch between a stable and an unstable configuration by modifying, for example, some properties of the angle. And we have the switching law sigma. I think discussing its effect, it's much easier by looking at the plot. And so let's do so. The vertical blue lines show when we're switching between one mode and the other. And so employing our control law and adaptive law, which again are the same, but in the carateri framework, we have certain guarantees, and the Filippov framework, we have other guarantees. We see that the black line converges to 0 in norm, converges to 0 fast, has some spikes here and there in response to the switches in the plant and in the reference model. Whereas if we decided to apply classical model reference adaptive control, which for fairness of comparison, we must highlight that it's not designed for classical, for switch systems, MRAC would struggle, especially when the switching occurs extremely fast. As we can see, around 25 seconds, there we have the equivalent of something like 1 over S, so basically 1 over T. So basically, the switchings occur faster and faster. In the limit, they go to 0. If we look at the control input, employing our approach, it's a scalar, so you can see that it stays bounded as expected. Clearly, the frequency of oscillation of U increases as the switching between the two sigmas, the two modes, gets faster and faster. If we employ classical MRAC, the control input would be of several orders of magnitude bigger. With our approach, it's in the order of 10 to the 2. Here, it's in the order of 10 to the 5. Again, a classical MRAC is not designed to handle these cases, but we're doing this comparison just to give you an idea about the performance of our approach. And so we applied this to a special aircraft. It's a so-called tilt rotor quadcopter. So it's a quadcopter for which we're able to tilt the spin axis of the 4 propellers so that it can basically, you can describe it in multiple ways. One way is that the aircraft can tilt while staying in place. Quadcopters are unable to do so. If a quadcopter pitches or rolls, then it moves sideways. This aircraft is able to pitch and remain in place because at the same time we can move the direction of the propellers. The task here is to install a camera on a wall. The camera is mounted at the end of a stick and is connected by a suction cup. So we need to press the camera against the wall, activate the suction cup, release the suction cup. The camera stays up using Velcro, and the vehicle will fly backward. The equations of motion here are given by the classical Euler and Newton's law, written in a slightly fancy form, but M is general mass matrix, the usual dynamics given by Coriolis and other terms in FD and Tran and FD Roth. Now, the interesting thing is that when we activate the suction cup and we're pressing the camera against the wall, the quadcopter or the tilt rotor vehicle instantaneously becomes a cantilever beam. And so we have 2 totally different systems, and yet we want to regulate them, and we don't inform the vehicle when the contact has happened. So all of a sudden, the controller will recognize that the system's behavior has changed, and we want it to do its job, so to keep pressing and keeping the aircraft leveled until we release the suction cup purposely. So if I really, okay, there you go. All right, so if we look at, I'm really sorry, I should have taken care of this. That's sponsored research for you. There you go. All right, so the aircraft takes off here. It's taking off from the red mat, and it's not supposed to go behind the red mat after the mission. So we're moving forward toward the wall, pressing against the wall. You see the propellers tilting a little bit forward, and then release the suction cup. And we don't want to go past the red line here. The constrained MRAC part would have helped even more. The aircraft is going down back to its position. Here is slow down version. As you can see, we're plotting the force almost synchronized with the aircraft motion. And here is a cantilever beam, basically. And all of a sudden here, it goes back and becomes a quadcopter. We did something similar. This work has been done, by the way, in collaboration with the Army Research Lab and the former Flight Control Directorate. And here we basically, Autonomous Vehicles Directorate, I'm sorry. We have an aircraft that is connected to a rope, and someone, without any notice, pulls the rope, and we want the aircraft to keep its pitch angle at 0 degrees, no matter what. All right, so let's go back to our slides. And here is a more recent work. It's about hybrid systems. And again, I'm aiming at model reference adaptive control for hybrid systems. Hybrid systems are a more general class of dynamical systems than switch systems, because not only the dynamics changes instantaneously, but we assume that also the state has instantaneous jumps. So a classical example, if you have a ball bouncing on a wall or on a hard surface, we all know that instantaneously, or at least on the time scales we are interested in, the direction of the velocity orthogonal to the surface reverses. And so the state vector, because this is a mechanical system, so the state vector comprises position and velocity, I was saying the state vector changes instantaneously. In this case, we introduce, or we leverage a another class of solutions that goes by the name of Krasovsky solutions, in which you create a regularization of the fields F and G, where F regulates the continuous time dynamics and G the discrete time dynamics. If you compare and contrast Krasovsky solution and Filippov solutions, the definitions are extremely similar. The only difference is that we don't have an intersection. We have only one intersection, not two. The missing intersection is over sets of measure 0, because otherwise we would be missing the instantaneous switching in the state. For these systems, to my knowledge and some other researchers' knowledge, until like this paper I'm referring to was published at the end of 2022, there was no version of LaSalle-Yoshizawa theorem for time-varying hybrid dynamical system. There are versions of LaSalle-Yoshizawa for time-invariant dynamical systems, for autonomous dynamical systems, hybrid, of course, but not for time-varying. So we worked on a generalization. I expect many others to exist out there. And so, first of all, I introduce so-called critical points relative to a function v that eventually will turn out to be the Lyapunov-like function, and a function w that is positively definite, sufficiently regular, and later it'll turn out to be the upper bound of on v dot. No? Negative w will be the upper bound of v dot. So, and I introduce these critical times T bar, that the first two, T naught and T1, T naught is the initial time, T1 is arbitrary, and from that point on are given basically by this formula, the first formula that you see at the center of the screen, the infimum of all the T's over the interval of existence, such that basically the integral of W is bigger than the sum of the jumps of V. Very roughly speaking, if you already see V as the Lyapunov function and W as the upper bound on V dot, we're comparing coarsely the integral of V without accounting for the jumps and the sum of the jumps of V due to the hybrid nature of the plant. So why do we need these points? We need them for to enunciate the theorem. If we have V comprised between two positive definite functions, W1 and W2, outside a set A that is compact and such that switchings don't occur in the interior of the set, and V dot is bounded by this non-negative and sufficiently regular function outside the set A, then, as in the classical LaSalle-Yoshizawa theorem, if I start close enough to this set A, or a bar to be, let's say, because it's a closed set, then eventually the trajectory converges to the set where the W's are equal to 0. In this recent paper of mine, we have also a version assuming that solutions are not maximal, and so we relax this condition of the limit for t that goes to infinity. But again, I'm trying to give more of an overview of results, and I'll be happy to discuss specifics or more detailed results after my presentation. A few remarks. So if A is equal to 0, then it's a single point, which is the equilibrium point. Then we go back to a formulation that is closer to the classical LaSalle-Yoshizawa theorem. And if W1 and W2 are radially unbounded, and the set in which the solution are supposed to exist is Rn, then we can suppress the assumption of starting close enough to the set A or the set 0 if you're all interested in convergence to 0, as in the classical LaSalle-Yoshizawa theorem. There's definitely an additional condition, which is the boundedness on the jumps of V, which I captured here in red. So we need to assume that this exists and is finite. All right, so when those of us who do adaptive control, when we see LaSalle-Yoshizawa, next thing we know, we're thinking about how to use it for proving convergence of our dynamicals, of our control system. So we have a plant that looks like the switch plant, but now we're also adding jumps, unknown, unexpected jumps in the plant, and a reference model, and now we reserve the right of adding jumps to the reference model. So basically, we want to control the system through an adaptive law, despite uncertainties in the model, despite uncertainties in the jumps of the plant, and an additional tuning knob for us will be the set of resetting events for the reference model and how the reference model jumps. So GDREF and the set DREF in green in the slide here. So the idea, roughly speaking, is the following: to continue having an adaptive gain that is absolutely continuous and designed as, for example, a Kara-Teodori solution of a switched but not hybrid adaptive law, and have a Lyapunov function that has pretty much the usual shape. P changes as RF changes, and it's the solution of the Lyapunov equation as usual. And we intentionally introduce switchings in the reference model so that the sum of the jumps in the Lyapunov function, that now only depends on E because delta theta is absolutely continuous, so any jumps in V can only come from E and it cannot come from the adaptive gain. I was saying we adapt all the jumps in V, and because the reference model will help bringing down the value of V, eventually we meet the condition of our version of LaSalle-Yoshizawa, whereby the series of all V has to be, of the jumps in V has to be, exist and has to be bounded. So here is the definition of the times at which the reference model switches, assuming that this condition is met, which means basically assuming that we have Qs that have sufficiently large, whose smallest eigenvalue is sufficiently large, but Q is user defined, so we can always crank this up, and we always crank those up at discrete times during the process, because at this point we're in classical MRAC, Q is fixed. Now the theoretical formulation allows us to change Q, and the jumps in the reference model are shown in this slide as well. So theorem statement, we have the usual shape at this point of the adaptive law and the usual shape of the adaptive gain, and then P, as usual, has to meet the reference, the Lyapunov equation. Super quickly to conclude, simple example, we have a ball that is has to stay within a rectangle that is given by the pink boundary, and has to follow P user path, and the P user path is drawn carelessly because it goes outside the pink rectangle, but the ball cannot penetrate the wall, so it's going to bounce off the wall. And so we introduce a reference model that is supposed to trace the user-defined path, but from time to time, because of these resetting events, it gets modified locally and helps basically the closed-loop plant trajectory to follow as closely as possible at least the path, despite the fact that the user-defined path is absolutely unfeasible. And here we have also a zoom in of our path. Interestingly enough, if we compare the L2 norm of the tracking error, to be precise here, I'm plotting the error between the position of the ball and the corresponding position on the path, so it's more a path following error. Our approach provides a much smaller L2 norm of the error. Again, these comparisons are given more for the sake of explaining the performance of our system against a standard baseline, which is classical MRAC, which again is not designed to address these weird situations. Likewise, the L2 norm of the control effort is considerably smaller. want to shout out thanks to the generations of students who've been helping me from undergraduate all the way to PhD level, and the funding agencies who and the collaborators at other universities who kindly pitched in this work and other aspects of my work that I haven't presented today. And with this, I would like to thank you once again, and I'm open to questions or suggestions. Thank you.
Thanks, Andrea, for the presentation. I really enjoyed. Am I hearing my voice? Okay.
There is a feedback.
Maybe not.
I don't hear a feedback, just in case.
Okay, perfect. I will try to talk, but yes, it's a funny fact. We were just talking with Tansel about the transient response improvement. Like we were talking, some of people, as you said, working on observer design or modifying the reference model, the reference model part of the system, or some of the people are coming up with the unique designs, as you find out, because these are really important for the practical applications. So thank you for all the information about this and the hybrid control part. Well, it's time to take questions. If you guys want to ask questions, you can just simply unmute yourself and ask, or you can put your questions to the chat box and we can read such that Andrea can answer your questions. Thank you very much.
So I can start. So Andrea, I am not going to ask technical work. I am already following your research, so which is great. And at some level, right? So it was also interfacing with set theoretic stuff that we have been developing. So your main application, I'm also amazed, like quadcouplers and other stuff that you have been doing. What other type of applications are you exploring in addition to quads?
It's been 1.5 year, couple of years that started going into ground vehicles, high-speed ground vehicles moving off-road. I explored more the trajectory planning aspect of this, but I do see a lot of room for potential on adaptive control in this area, especially off-road at high speed. If you have suspensions that are fairly elastic, so from time to time you may lose contact between the wheels that generate the force and the floor. We identified also that there is not much intersection between the controls community and the so-called terra mechanics community, which basically is the discipline that studies the tire terrain interaction. But they have many very good solutions on estimating the terrain parameters. And having this information to, for example, update your regressor vector or help some observer in case you're doing, auto feedback or doing data-driven, for example. That's an area that I find, to my knowledge at least, fairly underdeveloped. So we hope to be giving some contribution in the short term as well as the medium term in this area.
Thanks, Andrea.
Thanks. All right, guys.
All right, our audience is usual silence. So I'm glad you listed your email, Andrea, on the final slide. So for questions from the audience, can they email you?
Oh, absolutely. I'll be happy to, and I'll be happy to exchange ideas with colleagues as well as students.
Awesome. Merve, passing the ball to you.
First, I think there is no more questions. Thank you very much for your time and giving the seminar, and hope to see you soon.
All right. Thank you, guys. Bye.
Thanks, everyone.
Thanks, Andrea. I will share with you guys the link whenever Microsoft Teams gives it to me.